Chemical equilibrium. Most of the reactions do not undergo completion even if favorable experimental condition is provided. Only a zero order reaction goes to completion. A reaction will proceed to some extent and then stops virtually. All the observable properties of the system do not change when this state is reached. This is known as chemical equilibrium. A chemical equilibrium has the following criteria: approachability from both the ends, permanency of the equilibrium, incompleteness of the reaction, and dynamic nature of equilibrium. Let us try to explain these concepts considering the example of formation of HI from H to G and I to G in a closed container at 723 Kelvin. If we take 1 mole of H2G and 1 mole of I2G in a closed container at 723 Kelvin, then the reaction will proceed to some extent and will produce HI gas and stops virtually. This is known as chemical equilibrium, and the composition of the system do not undergo any change when this state is reached, and the equilibrium composition will remain unaltered for infinite period of time. And on the other hand, if we take 2 moles of HI gas in the closed container at the same above temperature of 723 Kelvin, then the HI gas will get dissociated to some extent and it will also attain the same equilibrium. So the chemical equilibrium can be approached from both ends, that is both from reactant end and product end. And once this equilibrium composition is reached, there will be no change in composition until the experimental conditions, temperature and pressures are getting altered. So a chemical equilibrium is permanent in that perspective. And the third one is that incompleteness of the reaction, that is when the chemical equilibrium is reached, neither the forward reaction nor the reverse reaction gets completed totally. And the chemical equilibrium is attained only when the rate of forward reaction becomes equal to the rate of reverse reaction. And the most important point here is the dynamic nature of chemical equilibrium, and it can be proved by using the radioactive isotope. Suppose in the given example of H2HI formation reactions, we have taken the equilibrium compositions of all the components. Only iodine is taken radioactive and all the components have been taken non-radioactive. Then it has been observed by the measurement, by the radioactivity measurement time to time, that the radioactivity of iodine is getting decreased while that of HI is getting increased. And the rate of decrease of radioactivity of iodine is equal to the rate of enhancement of radioactivity in HI. So this proves that the chemical equilibrium is dynamic in nature. Now let us come to the discussion of mass action law. This law was first formulated by C.M. Goldberg and P. Waage. It governs the effect of mass of reactant on rate of a chemical reaction. According to this law, the rate of a chemical reaction is directly proportional to the active mass of the reactant along with the respective stoichiometric coefficients at constant experimental conditions. Now, what is this active mass? Active mass is a thermodynamic property. For pure solid and liquids, this active mass is taken as constant and it is taken to be unity. For substances in solution, active mass is taken as the molar concentration of the substances, considering the solution to be dilute. And for gases reactant, the active mass is taken as the partial pressure of the component, provided the pressure is low. Now let us come to the application of this mass action law on chemical equilibrium. Let us consider a generalized chemical reaction as nu1a1 plus nu2a2 in equilibrium with nu3a3 and nu4a4. Here a1, a2 are reactant and a3, a4 are products. So nu1 is the stoichiometric coefficient of the component a1. So here, since A1 and A2 are reactants, so the rate of forward reactions can be written as active mass of A1 to the power nu1 into active mass of A2 to the power nu2 by applying mass action law. So Rf equals to Kf into A1 to the power nu1 into A2 to the power nu2, where Kf is the rate constant for the forward reaction. It depends on temperature and the nature of reacting species. And As time progresses, the concentration of A1 and A2 gets lowered while that of A3 and A4 gets enhanced. So the rate of reaction, reverse reaction gets increased, and applying mass action law, we can formulate the reverse reaction as follows. That is RB is proportional to A3 to the power nu 3 into A4 to the power nu 4. Therefore, RB equals to KB into A3 to the power nu 3 into A4 to the power nu 4, where KB is known as the rate constant for the reverse reaction. It also depends on temperature and the nature of products. Whenever the chemical equilibrium is reached, the rate of forward reaction should be equal to the rate of reaction. So we can equate this RF to RB, and then if we equate, then the final expression appears to be as follows. That is Kf by Kb equals to A3 to the power nu 3 into A4 to the power nu 4 divided by A1 to the power nu 1 into A2 to the power nu 2. Here Kf and Kb both are constant, so their ratio is also a constant, and that constant is known as equilibrium constant, and it is represented by capital K. Now, if we express the active mass in terms of partial pressure, then the equilibrium constant is known as Kp. If we express in terms of molar concentration, then the equilibrium constant is Kc. And if we express it in terms of mole fraction, then the equilibrium constant is expressed as Kx. And the interrelations between them, these are the interrelations. These are simple equations, that is Kp equals to Kc RT to the power del nu, where del nu is the summation of new product minus summation of new reactant. Kp equals to Kx into P to the power del nu, and Kc equals to Kx P by RT to the power del nu. These equations can be derived by utilizing very simple chemical equations. You can try it by yourselves. Now, these are very simple. Now, let us come to the classifications of chemical reactions. Chemical reactions can be of two types: homogeneous reactions, where all the reactants and products are in the same phase. So, just look at the examples. Here, all the reactants and products are in the gaseous phase. But in heterogeneous reactions, the reactants and products do not remain in same phase. Here, CaCO3 is in solid phase, whereas CaO is in solid phase, CO2 is in gas phase. Now, in this example, try to find out the value of del nu. What is del nu? Del nu is the summation of nu of HI, that is 2, minus summation of nu of reactant, that is summation of nu of H2, which is 1, and summation of nu of I2, which is 1. So here del nu is 0. In the second reaction, del nu is 1 plus 1 minus 1. That is positive, and here the del nu is 2 minus 1 minus 3. Here del nu is negative. Now let us try to apply the mass action law on chemical reaction. Let us consider that we have started with A moles of H2 gas and B moles of I2 gas. Then at equilibrium, the number of moles should be A minus X, B minus X, and that of HI should be 2X. If we try to express that in terms of concentration, then it would be at, if considering B to be the vessel volume, this expression should be A minus X by V, B minus X by V, and 2X by V. Then in terms of mole fraction means mole number of that constituent. Here H2 mole number is A minus X by total number of moles at equilibrium. That is A minus X plus B minus X minus 2X. And this total number of moles comes out to be A plus B. So similarly, mole fractions have been written for all the components. Then come to the partial pressure. What is partial pressure? That is mole fraction into total pressure. So I have written everything in this manner. So if I want to express Kp, what is Kp? Kp is partial pressure of Hi square divided by partial pressure of H2 into partial pressure of I2. Just I have put these expressions, I will obtain the final expression of Kp. Here Kx is mole fraction of Hi square divided by mole fractions of H2 into mole fractions of I2. Here is the expression, and this is the expression of Kc. Just look at this expression. These three expressions are equivalent. Why? Because here del nu is 0. So just look, consider the interrelations between Kp and Kc. Kp equals to Kc RT to the power del nu. So if del nu becomes 0, then Kp is equal to Kc and also equal to Kx. So all the values of Kp, Kc, and Kx will be the same. Now let us try to focus on the concept of degree of advancement of a reaction and chemical equilibrium. Let us consider a generalized reaction nu1A1 plus nu2A2. equilibrium with nu3a3 plus nu4a4. So we can write it in this fashion: 0 equals to summation over nu y ai, where nu y is the stoichiometric coefficient of the ith component, and this nu y value is negative for reactant and positive for the product. Now, the progress of the reaction can be quantitatively measured by a term called degree of advancement or extent of reaction, xi. Xi is always a positive quantity. If xi is 0, then the reaction is at the reactant side. That is at the start of the reaction. And if xi is 1, then the reaction is complete. That is at the product side. Now, let us suppose that Ni0 is the number of moles of the ith component initially and Ni the number of moles of the ith component at any time. Then the interrelations between Ni and Ni0 can be written as follows: Ni equals to Ni0 plus mu y xi. Therefore, dni comes out to be nu I dxi. Therefore, dxi can be written as dni by nu y. It is a very important relation. We will use it in a later. Now, try to focus on thermodynamic aspects of chemical equilibrium. For an open system, change in Gibbs free energy of the reaction, dg, can be written as minus of HTG plus VdP plus summation over mu I dni, where mu I is the chemical potential of the ith component. A reacting system is also an open system since the concentration gets altered during the progress of reaction. Now, at constant Tp condition, this first two terms gets vanished and dg at constant Tp comes out to be summation over mu y dni. Now here we will apply the expressions of dni to be nu y design as we have derived earlier. So the slope of g versus xi plot, that is del g del xi at constant Tp, comes out to be summation over nu I mu I. So if we try to write it in explicit expression, then it comes out to be minus of mu1 minus mu2 plus mu3 plus mu4 since the stoichiometric coefficient for reactants are negative and for products it is positive. So it comes out to be G3 plus G4, that is the summation of free energy of products minus G1 G2, that is summation of Gibbs free energy of reactant. So that is the del G, that is the free energy change of the reaction. And this free energy change of the reaction, it is nothing but the rate of change of Gibbs free energy per degree, with respect to degree of advancement of the reaction at constant temperature pressure condition. And if this slope is negative, that means del G is negative, the reaction is spontaneous. But if this slope is positive, that means the forward reaction is not spontaneous, then the reverse reaction will occur. And if this slope is 0, that means del G equals to 0, the reaction will be at equilibrium. Now this is the plot for G versus xi. Consider that here xi is always a positive quantity, so its value lie between 0 and 1. Here this slope value is negative. That means del G is negative, so reaction is spontaneous. Forward reaction is spontaneous. Here the slope is positive. That means forward reaction is not spontaneous, but reverse reaction is spontaneous. If we consider the previous reaction, then here the reaction will occur in this fashion that nu3a3 plus nu4a4 will get converted to nu1a1 plus nu2a2. And at this point here the slope is 0. That means the reaction is at equilibrium and the corresponding xi has been marked as xi equilibrium. Now this is the previous expression with which we are familiar with. That is, the expression comes out to be mu3 plus mu4 minus mu1 minus mu2. And in case of mixture of chemicals, mu can be written as mu equals to mu I0 plus RT ln AI, where mu I0 is the standard chemical potential value for the ith component. And if we write it in this manner, then the expression comes out to be del G equals to del G0, that is the free energy change at standard state, plus RT ln this value is the reaction quotient at any point of time during the reaction. And this is the most important reaction. It is known as the Van 't Hoff reaction isotherm. Now in this reaction, QA, that is the activity quotient at any point of time, and during chemical equilibrium, del G is 0. Therefore, del G0 is minus RT ln QA at equilibrium. And what is QA at equilibrium? This is nothing but the equilibrium constant, Ka. So del G0 is minus RT ln K, and if we substitute this expression here, the final form comes out to be del G is minus RT ln K plus RT ln QA. So here we can have three conditions, that if K greater than QA, then del G comes out to be negative, that means forward reaction is spontaneous. If K less than QA, then del G positive, that means reverse reaction is spontaneous. And if K equals to QA, then del G is 0, that means the reaction is at equilibrium. So too far we have a very basic concept on thermodynamics